Question 1. Which approach would be most effective for a service provider deploying Alcatel Lucent Virtual Private LAN services to ensure both technical performance and customer satisfaction across diverse enterprise clients? Option A. Focus exclusively on implementing the most cost-effective VPLS configuration available, assuming all clients will accept a standardized, basic service to minimize operational overhead. Option B. Prioritize a deep understanding of VPLS technical characteristics and their implications for traffic isolation and management, coupled with a detailed assessment of each client's specific business and technical requirements to tailor the service offering and associated service level agreements. Option C. Rely on generic network design principles without specific consideration for the unique Layer 2 nature and broadcast domain characteristics of VPLS, assuming standard troubleshooting methods will suffice. Option D. Implement VPLS with a broad range of advanced features and configurations, regardless of specific client needs, to offer a comprehensive, one-size-fits-all solution. The correct answer is B. Prioritize a deep understanding of VPLS technical characteristics and their implications for traffic isolation and management, coupled with a detailed assessment of each client's specific business and technical requirements to tailor the service offering and associated service level agreements. Explanation: this scenario is professionally challenging because it requires balancing the technical capabilities of Alcatel Lucent Virtual Private LAN Services, VPLS, with the diverse operational and business needs of different customer segments within a service provider's network. The service provider must ensure that the VPLS deployment not only meets the technical specifications, but also adheres to the regulatory framework governing telecommunications services, which in this context is assumed to be aligned with general principles of service provision and customer protection, without specific jurisdiction being mandated beyond the exam's scope. Careful judgment is required to avoid over-engineering or under-delivering, both of which can lead to customer dissatisfaction and potential regulatory scrutiny. The correct approach represents best professional practice because it prioritizes a thorough understanding of the underlying technology and its limitations in conjunction with a detailed analysis of customer requirements. This ensures that the VPLS solution is not only technically sound, but also strategically aligned with business objectives and customer expectations. By focusing on the specific service level agreements, SLAs, and the inherent characteristics of VPLS, such as its Layer 2 nature and the implications for traffic management and isolation, the service provider can proactively identify potential issues and design a robust, compliant, and efficient service. This aligns with the professional obligation to deliver services that are fit for purpose and meet agreed-upon standards, thereby fostering trust and long-term customer relationships. An incorrect approach that focuses solely on the lowest cost without considering the technical implications or customer needs would be professionally unacceptable. This could lead to a VPLS implementation that fails to meet performance requirements, lacks adequate traffic isolation between customers, or is difficult to manage, potentially violating implicit or explicit service commitments and leading to customer complaints. Another incorrect approach that prioritizes advanced features without a clear business justification or customer demand might result in unnecessary complexity and cost, failing to deliver tangible value and potentially misallocating resources. A third incorrect approach that ignores the specific characteristics of VPLS, such as its broadcast domain behavior, and attempts to apply solutions designed for other network architectures, would likely result in suboptimal performance and security vulnerabilities, again, failing to meet professional standards of care and due diligence. A professional decision-making process for similar situations should involve a structured approach. First, deeply understand the technology, Alcatel Lucent VPLS capabilities and limitations. Second, thoroughly assess customer needs and expectations, including their business criticality and technical requirements. Third, evaluate the regulatory landscape for any specific mandates related to service isolation, data privacy, or service quality. Fourth, design a solution that optimally maps technology capabilities to customer needs within the regulatory framework, prioritizing reliability, scalability, and cost-effectiveness. Finally, establish clear SLAs and monitoring mechanisms to ensure ongoing service quality and compliance. Question 2. The review process indicates that the proposed Alcatel Lucent Virtual Private LAN Services, VPLS, implementation for a new enterprise customer appears technically sound, but requires confirmation regarding its alignment with the Agreed-Upon Service Level Agreement, SLA, and the specific regulatory framework governing telecommunications services in the operating jurisdiction. Which of the following actions is the most critical step to ensure compliance and successful service delivery? Option A. Prioritize the fastest possible VPLS deployment to meet the customer's immediate business needs, with a plan to address SLA and regulatory compliance post-implementation. Option B. Verify that the VPLS configuration parameters, such as bandwidth, latency, and jitter, directly correspond to the metrics defined in the customer's SLA and confirm adherence to any relevant jurisdictional regulations for VPLS. Option C. Proceed with the VPLS deployment using the vendor's recommended default configuration, assuming it will meet general enterprise networking standards. Option D. Focus solely on the technical performance of the VPLS, assuming that meeting general network performance benchmarks will implicitly satisfy SLA and regulatory requirements. The correct answer is B. Verify that the VPLS configuration parameters, such as bandwidth, latency, and jitter, directly correspond to the metrics defined in the customer's SLA and confirm adherence to any relevant jurisdictional regulations for VPLS. Explanation. Scenario analysis. This scenario presents a professional challenge related to the implementation of Alcatel Lucent Virtual Private LAN Services, VPLS, within a specific regulatory environment. The core challenge lies in ensuring that the VPLS design and deployment adhere strictly to the defined service level agreements, SLAs, and the underlying regulatory framework governing telecommunications services. Misinterpreting or overlooking specific requirements can lead to non-compliance, service degradation, and potential penalties. The need for careful judgment arises from balancing technical feasibility with contractual obligations and regulatory mandates. Correct approach analysis. The correct approach involves a thorough understanding of the VPLS service requirements as defined by the customer's SLA and the relevant regulatory guidelines for VPLS deployment. This includes verifying that the proposed VPLS configuration, including parameters like bandwidth, latency, jitter, and packet loss, directly maps to the agreed-upon SLA metrics. Furthermore, it necessitates confirming that the chosen VPLS implementation adheres to any specific regulatory mandates concerning data privacy, service availability, or network resilience applicable to the jurisdiction. This approach represents best professional practice because it prioritizes compliance, customer satisfaction, and the integrity of the service. It demonstrates a commitment to delivering a service that not only meets technical specifications, but also legal and contractual obligations, thereby mitigating risks and building trust. Incorrect approach is analysis. An incorrect approach would be to assume that a standard VPLS configuration will automatically meet the SLA and regulatory requirements without explicit verification. This overlooks the critical step of mapping technical parameters to contractual and legal obligations. Failure to do so could result in delivering a service that technically functions, but fails to meet the performance guarantees stipulated in the SLA or violates specific regulatory stipulations, leading to contractual breaches and potential regulatory sanctions. Another incorrect approach would be to prioritize cost-effectiveness or speed of deployment over strict adherence to the SLA and regulatory framework. While efficiency is important, it cannot come at the expense of compliance. This approach risks overlooking critical VPLS parameters that are essential for meeting the SLA or regulatory mandates, potentially leading to service failures or noncompliance. A third incorrect approach would be to rely solely on vendor default settings for VPLS configuration without validating them against the specific SLA and regulatory context. Vendor defaults are generic and may not be optimized for the unique requirements of a particular customer or jurisdiction. This can lead to a VPLS service that is not fit for purpose, failing to meet performance targets or regulatory obligations. Professional reasoning. Professionals should employ a structured decision-making framework that begins with a comprehensive understanding of the project's requirements, including customer SLAs and all applicable regulatory frameworks. This should be followed by a detailed technical design phase, where VPLS parameters are explicitly mapped to these requirements. A rigorous validation and testing phase is crucial to confirm that the implemented VPLS meets all agreed-upon metrics and regulatory stipulations. Continuous monitoring and periodic reviews are also essential to ensure ongoing compliance and service quality. This systematic approach ensures that technical solutions are aligned with business objectives and legal obligations. Question 3. The analysis reveals that a network engineer is configuring an Alcatel Lucent VPLS service to connect multiple customer sites. The primary objective is to ensure seamless Layer 2 connectivity between these sites, mimicking a single bridge domain. Considering the core principles of VPLS as tested in the 4A0-105 exam, which of the following configuration strategies best aligns with establishing a robust and scalable VPLS instance? Option A. Configuring PE-to-PE pseudowires using a signaling protocol like LDP or BGP, ensuring that each PE router establishes a direct pseudowire to every other PE router participating in the same VPLS instance, and correctly mapping the VPLS instance to the appropriate LAN on the customer-facing interfaces. Option B. Relying solely on static configuration of pseudowires between PE routers without any dynamic signaling protocol, assuming that manual updates will be sufficient for network changes. Option C. Implementing VPLS by configuring only PE-to-CE customer edge connections and expecting the underlying network to automatically bridge traffic between customer sites without explicit PE-to-PE pseudowire establishment. Option D. Configuring VPLS by creating separate Layer 3 VPNs for each customer site and attempting to bridge traffic between these Layer 3 VPNs using complex routing policies. The correct answer is A. Configuring PE-to-PE pseudowires using a signaling protocol like LDP or BGP, ensuring that each PE router establishes a direct pseudowire to every other PE router participating in the same VPLS instance, and correctly mapping the VPLS instance to the appropriate VLAN on the customer-facing interfaces. Explanation. The analysis reveals a scenario where a network administrator is tasked with configuring Alcatel Lucent Virtual Private LAN Services, VPLS, to provide Layer 2 connectivity between multiple customer sites. The challenge lies in ensuring that the VPLS implementation adheres to the specific requirements of the 4A0-105 exam syllabus, which implicitly governs the expected knowledge and application of VPLS principles within the context of Alcatel Lucent equipment. This requires a deep understanding of VPLS concepts such as pseudowires, PE-PE connectivity, and the role of the provider edge P and provider P routers, all within the framework of the exam scope. The professional challenge is to select the most appropriate VPLS configuration method that aligns with best practices for scalability, manageability, and adherence to the underlying VPLS architecture as tested by the 4A0-105 exam. The correct approach involves understanding the fundamental principles of VPLS as implemented by Alcatel Lucent and how these principles translate into practical configuration. Specifically, it focuses on establishing PE-to-PE connectivity using appropriate signaling protocols and ensuring that the VPLS instance is correctly mapped to the underlying network infrastructure. This approach represents best professional practice because it demonstrates a thorough grasp of VPLS architecture, enabling efficient and reliable Layer 2 VPN services. It aligns with the exam's objective of assessing the candidate's ability to design and implement VPLS solutions that are robust and scalable. An incorrect approach might involve misinterpreting the role of different VPLS components, such as incorrectly configuring the pseudowire setup or failing to establish proper PE-to-PE signaling. This could lead to service disruption, connectivity issues, and an inability to meet customer requirements. Ethically, it represents a failure to competently apply the knowledge expected for the certification, potentially leading to a compromised network and a breach of professional responsibility. Another incorrect approach could be to oversimplify the configuration by neglecting essential VPLS elements, such as proper encapsulation or MTU settings, which, while seemingly efficient, would result in an unstable and non-compliant VPLS service. This demonstrates a lack of understanding of the critical dependencies within the VPLS framework, leading to a professionally unacceptable outcome. The professional decision-making process for similar situations should involve a systematic review of the VPLS requirements, a clear understanding of the Alcatel Lucent VPLS implementation details, as covered in the 4A0-105 syllabus, and a methodical approach to configuration. This includes verifying pseudo-wire establishment, ensuring correct signaling protocol operation, and validating the VPLS instance mapping to the underlying network. Professionals should always refer to official documentation and training materials relevant to the specific technology and certification being pursued. Question 4. The control framework reveals a customer is experiencing intermittent connectivity issues on a VPLS service. The network operations team has identified that the VPLS service is configured on Alcatel Lucent routers. Given the urgency to restore service, which of the following actions best aligns with professional best practices and regulatory adherence for managing this VPLS service incident? Option A. Proceed with a direct modification of the VPLS configuration on the affected PE routers based on a preliminary hypothesis, bypassing the formal change control process. Option B. Immediately revert the VPLS configuration to a previously known stable state without further investigation to restore service quickly. Option C. Engage internal VPLS subject matter experts, meticulously document the observed symptoms and configuration, and follow established troubleshooting and change management procedures for resolution. Option D. Escalate the issue directly to the Alcatel Lucent vendor support team without performing any initial internal diagnostics or documenting the observed behavior. The correct answer is B. Immediately revert the VPLS configuration to a previously known stable state without further investigation to restore service quickly. Explanation. Scenario analysis. This scenario presents a professional challenge related to the implementation of virtual private LAN services, VPLS, within a service provider's network, specifically concerning the adherence to established operational procedures and the potential impact on service integrity. The core difficulty lies in balancing the immediate need to resolve a customer-reported issue with the imperative to follow documented change management and testing protocols. Deviating from these established processes, even with good intentions, can introduce unforeseen risks, compromise network stability, and violate the service provider's own governance framework, which is designed to ensure consistent and reliable service delivery. The pressure to quickly restore service for a high-profile client can lead to shortcuts that undermine the long-term health and security of the network. Correct approach analysis. The correct approach involves meticulously documenting the observed behavior, cross-referencing it with the VPLS implementation guidelines, and Alcatel Lucent's best practices for the specific platform. This includes verifying the configuration of the provider edge, P routers, the virtual forwarding instances, VFI, and the underlying transport network. The next critical step is to engage the appropriate internal support teams, such as network engineering or a VPLS specialist, to collaboratively troubleshoot the issue. This collaborative approach ensures that the problem is addressed by individuals with the requisite expertise, and that the resolution aligns with established network architecture and operational standards. Following the documented troubleshooting and resolution procedures, including any necessary testing and validation before and after changes, represents best professional practice because it upholds the integrity of the network, minimizes the risk of unintended consequences, and ensures compliance with the service provider's internal policies and potentially any service-level agreements, SLAs, with the customer. This methodical approach fosters accountability and provides a clear audit trail for all actions taken. Incorrect approaches analysis. One incorrect approach involves immediately reverting the VPLS configuration to a previous known good state without thorough investigation. This is professionally unacceptable because it fails to identify the root cause of the problem, potentially masking an underlying issue that could recur or manifest in a different way. It also bypasses the opportunity to learn from the incident and improve future configurations. Ethically, it could lead to a recurrence of the service disruption, impacting customer trust and potentially violating SLA commitments. Another incorrect approach is to bypass the standard change control process and directly modify the VPLS configuration on the PE routers based on an assumption about the cause. This is a significant regulatory and ethical failure. It violates internal operational procedures designed to prevent network instability and unauthorized changes. Such actions can lead to unintended network outages, security vulnerabilities, and a lack of accountability, as there is no record of the change or its justification. This approach demonstrates a disregard for established governance and risk management practices. A third incorrect approach is to escalate the issue to a vendor support team without first performing basic internal diagnostics and documenting the observed symptoms. While vendor support is valuable, it is most effective when provided with comprehensive information. Failing to do so wastes valuable vendor time, delays resolution, and indicates a lack of internal due diligence. Professionally, it suggests an abdication of responsibility for initial problem solving and can lead to inefficient use of resources. Professional reasoning. Professionals facing such situations should employ a structured decision-making framework. This begins with a thorough understanding of the problem and its impact. Next, they should consult relevant documentation, including vendor guides, Alcatel Lucent in this case, internal network design documents, and operational procedures. The framework dictates that all troubleshooting and resolution steps should be performed within the established change management and incident management processes. Collaboration with subject matter experts and adherence to documented testing and validation protocols are paramount. If a deviation from standard procedure is contemplated, it must be rigorously justified, approved through a formal exception process, and its risks thoroughly assessed and mitigated. This systematic approach ensures that decisions are informed, defensible, and contribute to the overall stability and reliability of the network. Question 5. Governance review demonstrates that the deployed Alcatel Lucent Virtual Private LAN services, VPLS, are not consistently meeting the mandated quality of service, QoS, parameters as defined by the Telecommunications Regulatory Authority. Specifically, certain traffic classes are experiencing higher than acceptable latency and jitter, impacting the performance of time-sensitive applications for end users. The technical team is tasked with rectifying this situation. Considering the 4A0-105 Alcatel Lucent Virtual Private LAN Services syllabus and the implied regulatory framework, which of the following approaches best ensures immediate and sustainable compliance with QoS mandates? Option A. Increase the overall network bandwidth to alleviate congestion, assuming that improved capacity will inherently resolve the QoS issues without specific configuration adjustments. Option B. Implement a simplified VPLS configuration that prioritizes ease of management and operational efficiency, with the understanding that minor deviations from strict QoS parameters are acceptable for operational gains. Option C. Focus on optimizing the underlying physical network infrastructure, such as upgrading hardware, without directly addressing the VPLS QoS configuration, on the assumption that the VPLS is merely a symptom of a broader network problem. Option D. Reevaluate and reconfigure VPLS service instances to implement specific traffic policing and shaping policies, ensuring that bandwidth allocation and priority queuing align with the regulatory QoS specifications for each traffic class. The correct answer is D. Reevaluate and reconfigure VPLS service instances to implement specific traffic policing and shaping policies, ensuring that bandwidth allocation and priority queuing align with the regulatory QoS specifications for each traffic class. Explanation. Scenario analysis. This scenario presents a professional challenge related to the implementation of Alcatel Lucent Virtual Private LAN Services, VPLS, within a regulated telecommunications environment. The core challenge lies in ensuring that the chosen VPLS configuration adheres strictly to the defined quality of service, QoS, parameters mandated by regulatory bodies. Specifically in the context of the 4A0-105 exam's implied jurisdiction, which we will assume for this exercise, is a hypothetical jurisdiction with specific telecom regulations. The complexity arises from the need to balance technical feasibility, service-level agreements (SLAs), and compliance with potentially stringent QoS requirements that impact customer experience and competitive fairness. Misinterpreting or inadequately configuring QoS can lead to service degradation, customer complaints, and regulatory penalties. Correct approach analysis. The correct approach involves a thorough understanding of the 4A0-105 syllabus, focusing on how VPLS features can be configured to meet specific QoS objectives. This means leveraging Alcatel Lucent's VPLS capabilities to implement traffic policing, shaping, and prioritization mechanisms that align with the regulatory framework's CoS mandates. For instance, if regulations specify minimum bandwidth guarantees for certain traffic classes or maximum latency for real-time services, the configuration must explicitly address these. This approach represents best professional practice because it prioritizes compliance with regulatory mandates, ensuring that the deployed VPLS service meets the required performance standards. It demonstrates a proactive and informed application of technical knowledge to fulfill legal and ethical obligations, safeguarding both the service provider and its customers. Incorrect approach is analysis. An incorrect approach would be to prioritize ease of implementation or cost-effectiveness over strict adherence to CoS regulations. Example, selecting a default VPLS configuration without verifying its CoS compliance would be a regulatory failure. This neglects the explicit requirements of the governing framework, potentially leading to a service that does not meet mandated performance levels. Another incorrect approach would be to assume that standard VPLS features inherently satisfy all CoS requirements without specific validation against the regulatory framework. This demonstrates a lack of due diligence and a failure to understand the specific nuances of the applicable regulations. Ethically, this could be seen as a misrepresentation of service capabilities if the deployed service does not meet the promised or mandated quality. A further failure would be to implement CoS features in a manner that inadvertently creates unfair advantages or disadvantages for certain customer segments, violating principles of equitable service provision if such principles are enshrined in the regulations. Professional reasoning. Professionals tasked with VPLS deployment must adopt a decision-making framework that begins with a comprehensive review of the relevant regulatory framework and its specific CoS requirements. This should be followed by a detailed mapping of these requirements to the capabilities of the Alcatel Lucent VPLS solution, as detailed in the 4A0-105 syllabus. Configuration decisions must be driven by this mapping, with a strong emphasis on verification and testing to ensure compliance. A risk assessment should be conducted to identify potential CoS deviations and mitigation strategies. Documentation of the configuration choices and their rationale, referencing specific regulatory clauses, is crucial for auditability and accountability. Question 6. During the evaluation of a new VPLS deployment for multiple enterprise customers, what is the most critical consideration for ensuring the integrity and privacy of each customer's data traffic within the shared network infrastructure? Option A. Relying primarily on each customer to implement their own security protocols at their network edge to protect their data. Option B. Implementing robust traffic isolation mechanisms between distinct customer VPNs, ensuring no inter-customer data leakage. Option C. Deferring the implementation of advanced traffic isolation until a security incident involving inter-customer data access is reported. Option D. Utilizing a single, shared service instance for all customer VPNs to maximize network resource utilization and minimize operational costs. Correct answer is B. Implementing robust traffic isolation mechanisms between distinct customer VPNs, ensuring no inter-customer data leakage. Explanation. This scenario presents a professional challenge in network design and implementation, where a critical decision must be made regarding the isolation of customer traffic within a virtual private LAN service, VPLS, deployment. The core of the challenge lies in balancing the need for efficient resource utilization and network performance against the paramount requirement of customer data security and privacy, as mandated by regulatory frameworks governing telecommunications services. Misjudging the appropriate level of isolation can lead to significant security breaches, regulatory noncompliance, and severe reputational damage. The correct approach, which involves implementing strict traffic isolation between different customer VPNs within the VPLS, represents best professional practice because it directly aligns with the fundamental principles of VPLS service delivery and the regulatory expectations for private network services. VPLS is designed to emulate a Layer 2 switch domain, and a key benefit is the ability to provide private, isolated networks for each customer. Regulatory frameworks, even without explicit mention of specific UK/CISI or US regulations, universally emphasize the need for service providers to ensure the confidentiality and integrity of customer data. Implementing robust isolation mechanisms, such as distinct service instances or VLAN tagging strategies that prevent inter-customer traffic leakage, is a direct fulfillment of this obligation. This proactive measure minimizes the attack surface and prevents unauthorized access or interference between logically separate customer networks, thereby upholding service-level agreements and regulatory compliance. An incorrect approach that prioritizes cost savings by using a shared service instance without adequate logical separation for different customer VPNs is professionally unacceptable. This failure directly contravenes the implicit and often explicit regulatory requirement for data segregation and privacy in managed network services. Such a configuration creates a significant security vulnerability, where traffic from one customer could potentially be intercepted or influenced by another, leading to a breach of confidentiality and a violation of data protection laws. Ethically, it represents a dereliction of duty to protect customer data. Another incorrect approach, which relies solely on customer-implemented security measures at their network edge without provider-level isolation, is also professionally unsound. While customer-side security is important, the service provider has a fundamental responsibility to deliver a secure and isolated service. Delegating this responsibility entirely to the customer shifts the burden inappropriately and fails to meet the expected standard of a managed private network service. This can lead to regulatory scrutiny for failing to provide a secure infrastructure. A third incorrect approach, which involves implementing isolation only after a security incident is reported, demonstrates a reactive rather than a proactive security posture. This is a critical regulatory and ethical failure. Best practices and regulatory guidance consistently advocate for a preventative approach to security. Waiting for a breach to occur before implementing necessary isolation measures is a clear indication of inadequate risk management and a failure to uphold the duty of care owed to customers. The professional decision-making process for similar situations should involve a thorough risk assessment that considers the potential impact of security breaches and regulatory noncompliance. This assessment should be followed by the selection of design and implementation strategies that prioritize security and isolation as core service attributes, rather than as optional add-ons. Professionals should consult relevant industry best practices and any applicable regulatory guidelines to ensure their designs meet the highest standards of data protection and service integrity. A layered security approach, where the service provider implements robust isolation at the infrastructure level, is essential for building trust and ensuring compliance. Question 7. Strategic planning requires a network engineer to design a virtual private LAN service, VPLS, for a new client requiring Layer 2 connectivity between multiple geographically dispersed sites. The client has emphasized the need for strict traffic isolation between their sites and the ability to maintain a single broadcast domain for their internal network. The engineer is considering several approaches to meet these requirements. Which approach best aligns with the principles of VPLS and ensures a secure, scalable, and compliant solution? Option A. Extend the customer's existing VLAN tags directly across the provider network without VPLS encapsulation, relying on the customer's internal network to manage segmentation. Option B. Implement a VPLS instance using provider VLAN tagging PVLAN or equivalent mechanisms to encapsulate customer traffic and ensure isolation between different customer VPLS services, while mapping traffic from a single customer's sites into their designated VPLS instance to maintain a unified broadcast domain. Option C. Configure a Layer 3 VPN solution to connect the customer's sites, allowing for IP-based routing between locations. Option D. Establish individual point-to-point tunnels between each pair of customer sites to provide dedicated connectivity. The correct answer is B. Implement a VPLS instance using provider VLAN tagging, PVLAN, or equivalent mechanisms to encapsulate customer traffic and ensure isolation between different customer VPLS services, while mapping traffic from a single customer's sites into their designated VPLS instance to maintain a unified broadcast domain. Explanation. Scenario analysis. This scenario presents a professional challenge where a network engineer must balance the immediate operational needs of a client with the long-term implications of service design and adherence to established best practices within the Alcatel Lucent Virtual Private LAN Services (VPLS) framework. The pressure to deliver a quick solution for a critical business function can lead to shortcuts that compromise network integrity, scalability, and security. The engineer must exercise sound judgment to avoid introducing technical debt or violating the principles of VPLS as defined by the relevant standards and Alcatel Lucent's implementation guidelines, which are implicitly governed by the exam's jurisdiction. Correct approach analysis. The correct approach involves a thorough understanding of VPLS principles, specifically how to achieve traffic isolation and segmentation between different customer sites, while maintaining a single broadcast domain for each customer's LAN. This requires leveraging VPLS features like provider LAN tagging, PVLAN, or similar mechanisms to differentiate traffic from different customer sites at the provider edge, P, and ensure it is correctly mapped to the appropriate VPLS instance. This approach upholds the integrity of the VPLS service by ensuring that traffic from one customer's VPLS instance does not leak into another's, thereby maintaining the private aspect of the service and adhering to the fundamental design goals of VPLS for secure and isolated Layer 2 connectivity. It also considers the scalability and manageability of the solution, ensuring it can accommodate future growth and changes without significant rework. Incorrect approach is analysis. One incorrect approach would be to simply extend the customer's existing VLAN across the provider network without proper VPLS encapsulation. This fails to establish a true VPLS instance and would likely result in broadcast domain leakage, security vulnerabilities, and an inability to scale the service effectively for multiple customers. Violates the core concept of VPLS by not creating distinct, isolated Layer 2 VPNs. Another incorrect approach might be to use a generic Layer 3 VPN solution to connect the sites. While this provides connectivity, it fundamentally changes the service from a Layer 2 VPLS to a Layer 3 IP VPN. This would not meet the client's requirement for a private LAN service and would break the existing Layer 2 adjacency and broadcast domain requirements of their applications. A third incorrect approach could be to implement a point-to-point tunnel between each customer site. While this provides isolation, it is not a VPLS solution and does not create a single, logical Layer 2 broadcast domain across all sites for a given customer. This approach is inefficient, difficult to manage, and does not scale well for a large number of sites. Professional reasoning. Professionals should employ a structured decision-making process when designing VPLS solutions. This involves 1. Understanding the client's requirements thoroughly, including the need for Layer 2 connectivity, broadcast domain isolation, and scalability. 2. Consulting the relevant Alcatel Lucent VPLS documentation and best practices for the specific platform being used. 3. Evaluating potential solutions against the core principles of VPLS, ensuring traffic isolation, proper encapsulation, and efficient use of network resources. 4. Considering the operational impact, including manageability, monitoring, and troubleshooting. 5. Prioritizing solutions that offer robust security and scalability for future growth. 6. Documenting the design decisions and rationale, ensuring alignment with industry standards and vendor recommendations. Question 8. Cost-benefit analysis shows that implementing a virtual private LAN service, VPLS, solution for a new enterprise customer could be achieved through several architectural approaches, each with varying upfront capital expenditure and projected operational expenditure over a 5-year period. One approach offers the lowest initial hardware and software purchase price, but has a higher estimated annual maintenance cost and a moderate risk of service degradation during peak traffic. Another approach has a slightly higher upfront cost, but includes advanced traffic management features and a lower projected annual maintenance cost, with a low risk of service degradation. A third approach involves leveraging existing, albeit older, infrastructure with minimal new investment, but carries a significant risk of scalability limitations and increased troubleshooting time. Which approach represents the most professionally sound decision, considering the long-term implications for service reliability, customer satisfaction, and operational efficiency within the context of providing a robust and compliant VPLS service. Option A. The approach with a slightly higher upfront cost that includes advanced traffic management features and a lower projected annual maintenance cost, with a low risk of service degradation. Option B. The approach that prioritizes the lowest upfront capital expenditure without a detailed analysis of its long-term operational benefits and resilience features. Option C. The approach that leverages existing, older infrastructure with minimal new investment, despite its significant risk of scalability limitations and increased troubleshooting time. Option D. the approach with the lowest upfront capital expenditure, despite its higher projected annual maintenance costs and moderate risk of service degradation. Correct answer is D. The approach with the lowest upfront capital expenditure, despite its higher projected annual maintenance costs and moderate risk of service degradation. Explanation: scenario analysis. This scenario presents a common challenge in network service deployment, balancing the immediate cost savings of a less robust solution against the long-term risks and potential impact on service availability and customer satisfaction. The professional challenge lies in accurately quantifying intangible benefits like improved customer experience and reduced operational overhead from proactive issue resolution, and weighing them against the tangible, albeit potentially lower, upfront costs. Misjudging this balance can lead to significant financial and reputational damage, especially in a regulated environment where service continuity is paramount. Correct approach analysis. The correct approach prioritizes a comprehensive impact assessment that considers not only direct financial costs, but also the qualitative and long-term implications of network design choices. This aligns with best professional practice by advocating for a holistic view that includes service resilience, scalability, and the potential for future service evolution. From a regulatory perspective, particularly within the context of telecommunications services, demonstrating due diligence in ensuring service reliability and minimizing disruption is crucial. This approach ensures that decisions are informed by a thorough understanding of potential impacts on end users and adherence to service-level agreements, SLAs, which are often implicitly or explicitly governed by regulatory frameworks ensuring consistent service delivery. Incorrect approach is analysis. Focusing solely on the lowest upfront capital expenditure represents a failure to conduct a thorough impact assessment. This approach is professionally unacceptable because it ignores the total cost of ownership, including potential costs associated with increased downtime, emergency repairs, and customer churn due to poor service quality. Ethically, it can be seen as prioritizing short-term financial gains over the long-term well-being of the service and its users, potentially violating implicit or explicit commitments to service reliability. Opting for a solution with a slightly higher upfront cost, but without a detailed analysis of its long-term operational benefits and resilience features, is also flawed. While seemingly a middle ground, it lacks the rigor of a proper impact assessment. It risks overlooking critical factors that could lead to unforeseen operational burdens or an inability to meet future service demands, thus failing to demonstrate professional foresight and a commitment to optimal service delivery. Choosing a solution based on vendor familiarity alone, without a comparative impact assessment against alternatives, is a significant professional and ethical lapse. This approach is susceptible to bias and may lead to suboptimal outcomes. It fails to leverage competitive offerings or technological advancements that could provide better value or performance, and it bypasses the due diligence required to ensure the chosen solution truly meets the organization's and its customers' needs in the long run. Professional reasoning. Professionals should adopt a structured decision-making process that begins with clearly defining the objectives and constraints of the network service deployment. This involves identifying all relevant stakeholders and their expectations. A comprehensive impact assessment should then be conducted, evaluating technical feasibility, operational implications, financial viability, including both CAPEX and OPEX, scalability, security, and compliance with relevant regulations. This assessment should consider various scenarios, including potential failures and growth. The results of this assessment should then be used to compare different solution options, leading to a well-justified decision that balances immediate needs with long-term strategic goals and regulatory requirements. Question 9. Regulatory review indicates that a telecommunications provider is planning to deploy a new Alcatel Lucent Virtual Private LAN service, VPLS, to enhance its enterprise connectivity offerings. Which of the following approaches to assessing the impact of this VPLS deployment best aligns with ensuring regulatory compliance and minimizing operational risks? Option A. Deferring the impact assessment until after the VPLS has been fully deployed and is operational, to observe its real-world performance and address any issues as they arise. Option B. Performing a limited impact assessment focused solely on the VPLS technical performance metrics, deferring any regulatory compliance checks until after the service is live. Option C. Conducting a comprehensive impact assessment that evaluates technical performance, operational integration, security implications, and alignment with all applicable regulatory mandates for service availability and data privacy. Option D. Relying exclusively on the VPLS vendor's standard impact assessment documentation, assuming it covers all relevant regulatory considerations for the specific deployment region. The correct answer is C. Conducting a comprehensive impact assessment that evaluates technical performance, operational integration, security implications, and alignment with all applicable regulatory mandates for service availability and data privacy. Explanation. Scenario analysis. This scenario presents a professional challenge due to the inherent complexity of assessing the impact of a new virtual private LAN service, VPLS, deployment on existing network services, particularly when considering regulatory compliance. The challenge lies in anticipating potential service disruptions, performance degradation, or security vulnerabilities that could arise from the integration of VPLS, and ensuring these do not contravene the regulatory framework governing telecommunications services. A thorough impact assessment is crucial to proactively identify and mitigate risks before deployment, thereby safeguarding service continuity and customer satisfaction, and avoiding potential regulatory penalties. Correct approach analysis. The correct approach involves a comprehensive, multifaceted impact assessment that meticulously examines the technical, operational, and security implications of the VPLS deployment. This includes evaluating potential effects on existing traffic patterns, quality of service, CoS parameters, network resilience, and interoperability with other network elements. Furthermore, it necessitates a review of how the VPLS implementation aligns with the specific regulatory requirements for data privacy, service availability, and network security, as mandated by the relevant jurisdiction's telecommunications authorities. This proactive and detailed analysis ensures that the VPLS deployment adheres to all legal and operational standards, minimizing risks and demonstrating due diligence. Incorrect approaches analysis. One incorrect approach is to solely focus on the technical feasibility and performance metrics of the VPLS without considering its broader impact on existing services and regulatory obligations. This oversight can lead to unforeseen service degradations or compliance breaches. Another incorrect approach is to rely on vendor-provided impact assessments without independent verification, which may not adequately address the specific operational environment or the nuances of the local regulatory landscape. A third incorrect approach is to defer the impact assessment until after the VPLS is deployed, which is reactive and significantly increases the risk of service disruption and regulatory noncompliance, making remediation efforts more costly and complex. Professional reasoning. Professionals should adopt a structured, risk-based approach to impact assessment. This involves clearly defining the scope of the assessment, identifying all relevant stakeholders, and systematically evaluating potential impacts across technical, operational, security, and regulatory domains. Prioritization of risks based on their likelihood and severity, followed by the development of mitigation strategies, is essential. Continuous monitoring and reassessment throughout the deployment lifecycle are also critical to ensure ongoing compliance and service integrity. Question 10. Operational review demonstrates that a planned upgrade to the core network infrastructure, involving the introduction of a new traffic engineering protocol, is imminent. While the upgrade is expected to enhance overall network efficiency, there is a concern that it might inadvertently affect the performance and stability of existing virtual private LAN services, VPLS, deployments. Which of the following approaches best ensures the integrity of VPLS services during this upgrade? Option A. Implement the upgrade using vendor default configurations for the new traffic engineering protocol, assuming they are optimized for all network services, including VPLS. Option B. Conduct a detailed, VPLS-specific impact assessment to analyze how the new traffic engineering protocol will interact with VPLS forwarding mechanisms, pseudo-wire management, and MAC address learning, and perform pre-upgrade testing in a controlled environment. Option C. Form a general network impact assessment focusing on IP routing and bandwidth, and assume that VPLS, being a Layer 2 service, will not be significantly affected by changes at the IP layer. Option D. Proceed with the upgrade as scheduled, relying on the general network performance improvements to indirectly benefit VPLS and address any VPLS-related issues reactively after the upgrade is complete. The correct answer is B. Conduct a detailed VPLS-specific impact assessment to analyze how the new traffic engineering protocol will interact with VPLS forwarding mechanisms, pseudo-wire management, and MAC address learning, and perform pre-upgrade testing in a controlled environment. Explanation. Scenario analysis. This scenario presents a common challenge in network operations where a planned change, intended to improve service, has unforeseen negative consequences on existing virtual private LAN services, VPLS. The professional challenge lies in balancing the benefits of new technology adoption with the critical need to maintain the integrity and performance of established services, especially those that are revenue-generating or mission-critical for customers. The pressure to innovate and upgrade infrastructure must be tempered by a rigorous impact assessment process to prevent service disruption and customer dissatisfaction. The complexity arises from the interconnected nature of network services and the potential for cascading failures. Correct approach analysis. The correct approach involves a comprehensive pre-implementation impact assessment specifically tailored to VPLS services. This means meticulously analyzing how the proposed network upgrade, including any changes to routing protocols, encapsulation methods, or control plane mechanisms, will affect the Layer 2 forwarding behavior, MAC address learning, and traffic forwarding paths within the VPLS domains. It requires simulating the changes in a lab environment or using network modeling tools to predict potential issues such as increased latency, packet loss, control plane instability, or incorrect traffic steering for VPLS traffic. Adherence to Alcatel Lucent's best practices and documented VPLS deployment guidelines, which are implicitly part of the 4A0-105 exam scope, is paramount. This proactive approach ensures that potential disruptions are identified and mitigated before they impact live services, thereby upholding service-level agreements, SLAs, and maintaining customer trust. Incorrect approaches analysis. Implementing the upgrade without a specific VPLS impact assessment is a significant regulatory and ethical failure. It demonstrates a disregard for the potential consequences on existing services, which could lead to breaches of contractual obligations, SLAs, and regulatory noncompliance if service disruptions are severe enough to warrant reporting. This approach prioritizes technological advancement over customer service and operational stability, deploying the upgrade based solely on general network performance metrics without considering the unique Layer 2 forwarding and control plane characteristics of VPLS, also professionally unacceptable. VPLS relies on specific mechanisms for pseudo-wire establishment and MAC address learning that differ from IP routing. A generic assessment will miss VPLS-specific vulnerabilities. This failure to understand the nuances of the technology can lead to unexpected service degradation or outages. Relying on vendor default configurations for the new technology without validating their compatibility with the existing VPLS environment is another critical error. While vendor defaults are designed for general use, they may not be optimized or even compatible with specific VPLS implementations or customer configurations, leading to unforeseen issues. This approach abdicates responsibility for due diligence and can result in significant service impact. Professional reasoning. Professionals should adopt a structured, risk-based approach to network changes. This involves 1. Identifying all services potentially impacted by the proposed change. 2. For each service, conducting a detailed impact assessment considering the specific protocols, technologies, and configurations involved. For VPLS, this means understanding its Layer 2 forwarding, pseudo-wire management, and control plane interactions. 3. Prioritizing assessments based on service criticality and potential impact severity. 4. Developing and executing a comprehensive testing plan, including pre-change validation, during change monitoring, and post-change verification. 5. Establishing rollback procedures in case of unforeseen issues. 6. Documenting all assessments, tests, and outcomes. Question 11. The control framework reveals a proposed modification to an existing Alcatel Lucent Virtual Private LAN Service, VPLS, implementation. The modification is intended to enhance performance, but lacks a detailed analysis of its potential downstream effects on customer connectivity and service availability. Which approach best mitigates the risks associated with this change? Option A. Implement the change during a scheduled maintenance window without any prior assessment, relying on rollback procedures if issues arise. Option B, proceed with the modification immediately, assuming the vendor's documentation guarantees a seamless integration and minimal disruption. Option C, perform a quick review of the VPLS configuration files, focusing only on the immediate parameters being changed, and then implement the modification. Option D, conduct a comprehensive impact assessment by analyzing the VPLS configuration, identifying all affected customer sites and services, and simulating the proposed change in a controlled environment. The correct answer is D. Conduct a comprehensive impact assessment by analyzing the VPLS configuration, identifying all affected customer sites and services, and simulating the proposed change in a controlled environment. Explanation: scenario analysis. This scenario presents a professional challenge because it requires a network engineer to assess the impact of a proposed change to a virtual private LAN service, VPLS, implementation without a clear understanding of the downstream dependencies and potential service disruptions. The pressure to implement quickly, coupled with the lack of comprehensive impact assessment, creates a risk of unintended consequences that could affect multiple customers and violate service-level agreements, SLAs. The engineer must balance the need for operational efficiency with the imperative to maintain service integrity and customer trust. Correct approach analysis. The correct approach involves conducting a thorough impact assessment by analyzing the VPLS configuration, identifying all affected customer sites and services, and simulating the proposed change in a controlled environment or a lab setting. This proactive measure ensures that potential issues are identified and mitigated before deployment. This aligns with best professional practices by prioritizing service stability and customer satisfaction, which are implicitly governed by the principles of responsible network operation and adherence to contractual obligations, SLAs, that are fundamental in telecommunications service provision. While specific regulations for VPLS impact assessment might not be explicitly detailed in a single document for this exam, the underlying principle of due diligence and risk management is a cornerstone of professional conduct in regulated industries. Incorrect approach is analysis. Implementing the change directly without any form of impact assessment is a significant regulatory and ethical failure. It demonstrates a disregard for due diligence and a failure to uphold the implicit duty of care owed to customers. This approach risks violating SLAs, leading to financial penalties and reputational damage. It also bypasses established operational procedures designed to ensure network stability. Performing a superficial review of the VPLS configuration without considering the broader network context or customer-specific service requirements is also professionally unacceptable. This approach might miss critical interdependencies or edge cases, leading to unforeseen service degradations. It represents a failure to apply a comprehensive and systematic risk assessment methodology. Relying solely on the vendor's documentation for impact assessment, without independent verification or consideration of the specific network deployment, is another flawed approach. Vendor documentation may not account for unique configurations, customizations, or the specific operational environment, leading to an incomplete understanding of the potential impact. This demonstrates a lack of independent professional judgment and due diligence. Professional reasoning. Professionals should adopt a systematic approach to change management, beginning with a clear understanding of the proposed change and its objectives. This should be followed by a comprehensive impact assessment that considers all potential effects on services, customers, and the network infrastructure. Utilizing a risk assessment framework, including simulation and testing where feasible, is crucial. Documentation of the assessment process and its findings is essential for accountability and future reference. In situations of uncertainty or high risk, seeking consultation from senior engineers or subject matter experts is a sign of professional maturity and responsible decision-making. Question 12. Implementation of a new virtual private LAN service, VPLS, for a key enterprise customer is imminent. The network engineering team has proposed a configuration based on vendor best practices, but the operations team has raised concerns about potential impacts on existing traffic engineering policies and the security posture of the core network. The business unit is eager for the service to be activated within the week to meet a critical client deadline. Which approach best balances the immediate business need with long-term network stability and security? Option A. Halt the implementation and initiate a comprehensive impact assessment involving network engineering, operations, and security teams to identify and mitigate potential risks before proceeding. Option B. Implement the VPLS service using a minimal configuration that meets the basic requirements, with plans to enhance it later after the deadline has passed. Option C. Delegate the decision to the vendor's technical support team, trusting their expertise to ensure a smooth and secure implementation without further internal review. Option D. Proceed with the VPLS implementation immediately as proposed by the vendor, deferring any operational concerns to a post-implementation review to meet the client deadline. Correct answer is D. Proceed with the VPLS implementation immediately as proposed by the vendor, deferring any operational concerns to a post-implementation review to meet the client deadline. Explanation. The scenario presents a common challenge in network service deployment, balancing the immediate need for service activation with the long-term implications of network design and operational efficiency. The professional challenge lies in making a decision that satisfies business requirements without compromising the integrity, security, or future scalability of the virtual private LAN service, VPLS, implementation. This requires a thorough understanding of the VPLS architecture, its impact on the underlying network, and the potential downstream consequences of design choices. The correct approach represents best professional practice because it prioritizes a comprehensive impact assessment before proceeding with implementation. This involves evaluating how the proposed VPLS configuration will affect existing network services, traffic patterns, security policies, and operational procedures. By engaging relevant stakeholders and conducting thorough testing, this approach ensures that potential conflicts or performance degradations are identified and mitigated proactively. This aligns with the principles of responsible network engineering, which emphasize due diligence, risk management, and adherence to established best practices for service deployment. The regulatory framework for telecommunications services, while not explicitly detailed in the prompt for this exam, generally mandates that service providers operate in a manner that ensures service reliability, security, and fair access, all of which are supported by a robust impact assessment process. An incorrect approach that bypasses a formal impact assessment or relies solely on vendor recommendations without independent validation fails to meet professional standards. Such an approach risks introducing unforeseen issues, such as service disruptions for other customers, security vulnerabilities, or performance bottlenecks that could lead to service-level agreement, SLA breaches. Ethically, it is a failure to exercise due diligence and to act in the best interest of the customer and the overall network stability. Relying on a single department's perspective without cross-functional input can lead to siloed decision-making, overlooking critical interdependencies. This can result in a technically functional but operationally inefficient or insecure VPLS deployment, potentially leading to increased support costs and reputational damage. The professional decision-making process for similar situations should involve a structured approach. 1. Define the scope and objectives of the VPLS implementation. 2. Identify all potential impacts on the existing network infrastructure, services, and operations. 3. Engage all relevant stakeholders, e.g., network operations, security, customer support, business units. 4. Conduct a risk assessment to identify potential issues and their severity. 5. Develop mitigation strategies for identified risks. 6. Document the impact assessment findings and propose solutions. 7. Obtain necessary approvals before proceeding with implementation. 8. Plan for post-implementation monitoring and validation. Question 13. Quality control measures reveal an upcoming upgrade to the core transport network that provides the underlying connectivity for multiple virtual private LAN services, VPLS, deployments. Which of the following approaches represents the most professional and responsible method for ensuring VPLS service continuity during this upgrade? Option A. Perform a limited impact assessment focusing only on the VPLS control plane protocols, as this is the primary mechanism for VPLS establishment. Option B. Conduct a thorough impact assessment that analyzes the effects of the core network upgrade on the VPLS control plane, data plane, underlying transport and management systems, developing mitigation strategies for identified risks. Option C. Proceed with the core network upgrade as scheduled, assuming that changes to the transport layer will not affect the VPLS service, as VPLS operates at a different layer. Option D. Rely exclusively on the vendor's provided documentation for the core network upgrade to understand any potential implications for VPLS services. Correct answer is B. Conduct a thorough impact assessment that analyzes the effects of the core network upgrade on the VPLS control plane, data plane, underlying transport and management systems, developing mitigation strategies for identified risks. Explanation. Scenario analysis. This scenario presents a professional challenge because it requires a proactive and systematic approach to identifying potential disruptions to a critical service. The challenge lies in anticipating how changes in underlying network infrastructure, even those seemingly unrelated to the direct operation of virtual private LAN services, VPLS, could impact service availability and performance. A failure to conduct a thorough impact assessment could lead to unexpected service degradations, customer dissatisfaction, and potential breaches of service-level agreements, SLAs, all of which have significant business and regulatory implications. The complexity arises from the interconnected nature of modern networks and the need to understand dependencies. Correct approach analysis. The correct approach involves a comprehensive impact assessment that considers all potential points of failure and their cascading effects on VPLS. This includes evaluating the proposed network upgrades' effect on the underlying transport network, control plane protocols, e.g., BGP, LDP, data plane forwarding mechanisms, and any associated management or monitoring systems. By meticulously analyzing these dependencies, potential risks can be identified and mitigated before the upgrade is implemented. This aligns with the principles of robust network design and operational excellence, which are implicitly expected under general telecommunications regulatory frameworks that emphasize service continuity and reliability. Proactive risk management is a cornerstone of responsible service provision. Incorrect approaches analysis. One incorrect approach involves proceeding with the upgrade without any assessment, assuming that changes to the core network will not affect VPLS. This is a direct failure of due diligence and demonstrates a disregard for potential service disruption. It violates the implicit regulatory expectation of providing a stable and reliable service. Ethically, it is irresponsible to deploy changes without understanding their impact on customers. Another incorrect approach is to only assess the impact on the VPLS control plane, neglecting the data plane and the underlying transport. This is an incomplete assessment. While the control plane is crucial, data plane forwarding issues or transport network congestion can equally lead to VPLS service failure. This partial assessment risks overlooking critical failure points, leading to service outages and contravening the expectation of comprehensive service assurance. A third incorrect approach is to rely solely on vendor documentation for the upgrade, without performing an independent impact analysis specific to the deployed VPLS configuration. Vendor documentation may not account for specific network topologies, configurations, or existing operational constraints. This over-reliance can lead to unforeseen compatibility issues and service disruptions, failing to meet the professional standard of verifying changes within one's own operational environment. Professional reasoning. Professionals should adopt a structured risk management framework. This involves 1. Defining the scope of the assessment, clearly identifying the VPLS service and its dependencies. 2. Identifying potential risks associated with the proposed network upgrade, considering all layers of the network. 3. Analyzing the likelihood and impact of each identified risk. 4. Developing mitigation strategies for high-priority risks. 5. Documenting the assessment and mitigation plan. 6. Obtaining necessary approvals before proceeding with the change. This systematic process ensures that potential issues are addressed proactively, minimizing service disruption and maintaining customer trust. Question 14. Market research demonstrates a growing demand for enhanced bandwidth and differentiated services among enterprise customers. Alcatel Lucent's Virtual Private LAN Services, VPLS, is being considered for deployment to meet these needs. Which of the following approaches best represents a professional and compliant strategy for assessing the potential impact of introducing VPLS on the existing network infrastructure and current customer services? Option A. Prioritize the technical configuration and activation of VPLS for new customers only, without a formal assessment of its interaction with the existing network or services for current customers. Option B. Immediately deploy VPLS across the entire network to capitalize on the market demand and gather real-time performance data from all customers. Option C. Conduct a comprehensive simulation and pilot deployment in a controlled lab environment, followed by a phased rollout to a limited set of customers, with continuous monitoring and performance analysis before full-scale deployment. Option D. Rely exclusively on the vendor's provided VPLS implementation guides and assume no significant impact on existing services due to the inherent nature of VPLS. The correct answer is C. Conduct a comprehensive simulation and pilot deployment in a controlled lab environment, followed by a phased rollout to a limited set of customers, with continuous monitoring and performance analysis before full-scale deployment. Explanation: this scenario presents a professional challenge due to the inherent complexity of assessing the impact of new service deployments on existing network infrastructure and customer services, particularly within the context of virtual private LAN services, VPLS. The challenge lies in accurately predicting potential disruptions, performance degradation, and security vulnerabilities without causing actual service interruptions during the assessment phase. Careful judgment is required to balance the need for thorough evaluation with the imperative to maintain service stability and customer satisfaction. The correct approach represents best professional practice because it prioritizes a systematic, phased, and non-disruptive impact assessment. This involves detailed planning, simulation, and testing in controlled environments before live deployment. This methodology aligns with the principles of robust network engineering and service management, aiming to minimize risk and ensure service quality. Specifically, it adheres to the implicit regulatory expectation of service providers to operate with due diligence, ensuring that new services do not negatively affect existing ones and that customer expectations for reliability are met. This proactive stance is crucial for maintaining trust and compliance with service-level agreements, SLAs, which are often underpinned by regulatory requirements for service availability and performance. An incorrect approach that involves immediate, full-scale deployment without prior impact assessment is professionally unacceptable. This would represent a significant regulatory and ethical failure by exposing existing customers to potential service degradation or outages, thereby violating implicit obligations to maintain service continuity and potentially breaching contractual SLAs. Such an approach demonstrates a lack of due diligence and a disregard for customer impact, which could lead to regulatory scrutiny, fines, and reputational damage. Another incorrect approach, focusing solely on technical feasibility without considering the broader operational and customer impact, is also professionally flawed. While technically sound, it overlooks critical aspects of service delivery, such as performance monitoring, security implications, and the potential for cascading failures. This oversight can lead to unforeseen issues post-deployment, impacting customer experience and potentially violating regulatory requirements related to service resilience and security. A third incorrect approach, relying solely on vendor documentation without independent validation or testing, is professionally risky. Vendor documentation, while informative, may not fully account for specific network configurations, traffic patterns, or integration complexities unique to the service provider's environment. This can lead to an incomplete understanding of potential impacts, increasing the likelihood of unexpected problems, and failing to meet the professional standard of thoroughness expected in network service deployment. The professional decision-making process for similar situations should involve a structured risk assessment framework. This begins with clearly defining the scope of the new service and its potential interactions with existing infrastructure. Subsequently, a detailed impact assessment plan should be developed, outlining methodologies for testing, simulation, and validation. This plan should prioritize non-disruptive techniques such as lab testing, pilot deployments, and phased rollouts. Continuous monitoring and feedback loops are essential throughout the process to identify and address any emerging issues promptly. Adherence to industry, best practices, and regulatory guidelines for service deployment and management should be a guiding principle at every stage. Question 15. The evaluation methodology shows that a client requires a virtual private LAN service, VPLS, to connect multiple geographically dispersed sites, with a strong emphasis on ensuring that traffic from one customer site cannot be seen or accessed by another customer site within the same VPLS deployment. The client has expressed concern about potential traffic snooping between their own sites. Considering the Alcatel Lucent VPLS implementation and the need for robust Layer 2 isolation, which of the following approaches best addresses the client's requirement for site-to-site traffic segregation while maintaining operational efficiency and adhering to service design principles? Option A. Implement ISEC tunnels over the VPLS to encrypt traffic between all customer sites, thereby preventing any unauthorized access. Option B. Create a separate VPLS instance for each individual customer site to ensure complete isolation between all connected locations. Option C. Utilize MPLS VPN, Layer 3 VPNs, instead of VPLS, as they offer superior traffic isolation through routing table separation. Option D. Configure a single VPLS instance and rely on the inherent Layer 2 isolation mechanisms of VPLS, such as MAC address learning and ingress filtering, to prevent intersite traffic leakage. Correct answer is D. Configure a single VPLS instance and rely on the inherent Layer 2 isolation mechanisms of VPLS, such as MAC address learning and ingress filtering, to prevent intersite traffic leakage. Explanation. Scenario analysis. This scenario presents a common challenge in network design and implementation, where a client's perceived security needs might not align with the most efficient or compliant technical solution. The challenge lies in balancing the client's desire for granular control and perceived security with the practicalities of implementing and managing a virtual private LAN service, VPLS, solution within the Alcatel Lucent framework, adhering to relevant regulatory guidelines. Misinterpreting or over-engineering security can lead to increased complexity, operational overhead, and potential performance degradation, all while potentially failing to address the actual security risks. The professional must navigate the client's expectations, technical feasibility, and regulatory compliance. Correct approach analysis. The correct approach involves a thorough understanding of VPLS capabilities and limitations, specifically how it provides Layer 2 VPN isolation. It emphasizes leveraging the inherent security features of VPLS, such as MAC address learning and ingress filtering, segment traffic, and prevent unauthorized communication between customer sites connected to the same VPLS instance. This approach aligns with best practices by focusing on a secure and efficient design that meets the client's core requirement of isolation without unnecessary complexity. It also implicitly adheres to regulatory frameworks that mandate data segregation and protection by utilizing the service's design capabilities. The professional demonstrates best practice by proposing a solution that is technically sound, operationally manageable, and compliant with the service's intended use and underlying principles of network security. Incorrect approaches analysis. Implementing separate VPLS instances for each customer site, even if they are part of the same logical network, represents an over-engineered and inefficient solution. This approach fails to leverage the fundamental isolation provided by a single VPLS instance and introduces significant management overhead. From a regulatory perspective, while it might appear to enhance security through isolation, it doesn't necessarily offer superior protection compared to a well-configured single VPLS, and can lead to misconfiguration risks due to increased complexity. Proposing the use of ISEC tunnels over the VPLS to encrypt traffic between customer sites is also an incorrect approach in this context. VPLS inherently provides Layer 2 isolation, meaning traffic from different customer sites within the same VPLS instance is already segregated at the data link layer. Adding ISEC encryption at this stage is redundant for the stated requirement of isolation and adds unnecessary processing overhead and complexity to the network. It fails to recognize that VPLS itself is the mechanism for achieving the desired separation, and further encryption at this layer is not the primary or most efficient solution for Layer 2 isolation. Question 16. Investigation of a VPLS deployment scenario where a service provider is offering dedicated Layer 2 connectivity to multiple enterprise customers over a shared optical infrastructure. The provider must ensure strict isolation of each customer's Layer 2 broadcast domain to prevent any traffic leakage or unauthorized access between them. Which of the following approaches best guarantees this required traffic isolation within the VPLS framework? Option A. Assigning unique VLAN ID to each customer's access ports and ensuring these VLAN are terminated at the provider edge, not extended into the core network. Option B. relying on customer-provided encryption for all traffic traversing the VPLS, assuming this will inherently segregate their data. Option C, utilizing a single, common LAN ID for all customer access ports to simplify configuration across the provider network. Option D, implementing IP-based access control lists, ACL, at the provider edge to filter traffic between customer segments. The correct answer is A, assigning unique VLAN ID to each customer's access ports and ensuring these VLAN are terminated at the provider edge, not extended into the core network. Explanation: this scenario presents a professional challenge due to the critical nature of network segmentation and traffic isolation in a multi-tenant virtual private LAN service (VPLS) environment, ensuring that customer traffic remains segregated and that unauthorized access or interference is prevented is paramount for maintaining service integrity, customer trust, and compliance with service-level agreements (SLAs). The complexity arises from the potential for misconfiguration or design flaws to inadvertently bridge customer networks, leading to security breaches, performance degradation, and potential regulatory violations if sensitive data is exposed. Careful judgment is required to select the most robust and secure method for achieving this isolation. The correct approach represents best professional practice because it directly addresses the fundamental requirement of VPLS for logical separation of customer traffic within a shared infrastructure. By utilizing distinct VLAN ID for each customer's access ports and ensuring these VLAN are not propagated beyond the customer's demarcation point into the service provider's core network, it enforces strict traffic isolation. This aligns with the principles of secure network design and the operational requirements of VPLS, where each customer's Layer 2 domain is intended to be independent. This method is inherently secure, scalable, and minimizes the risk of inter-customer interference, thereby upholding contractual obligations and industry best practices for managed services. An incorrect approach that involves using the same VLAN ID for multiple customers across different access ports, without proper segmentation at the provider edge, represents a significant regulatory and ethical failure. This would lead to a direct violation of the principle of traffic isolation, potentially exposing customer data to unauthorized access and creating a security vulnerability. Ethically, it breaches the trust placed in the service provider to maintain confidentiality and integrity of customer traffic. Another incorrect approach, such as relying solely on IP-based access control lists, ACL, at the provider edge to segregate traffic, is insufficient for VPLS. VPLS operates at Layer 2, and while IP ACLs can filter traffic at higher layers, they do not inherently prevent Layer 2 broadcast or multicast traffic from intermingling between customers if the underlying VLAN segmentation is flawed. This failure to address the Layer 2 isolation requirement is a technical and professional oversight that could lead to service disruptions and security incidents. A professional decision-making process for similar situations should involve a thorough understanding of the VPLS architecture and its security implications. Professionals must prioritize solutions that provide robust Layer 2 isolation from the outset. This involves a risk-based assessment, considering the potential impact of misconfigurations or design flaws on customer data and service availability. Adherence to vendor best practices, industry standards for network security, and the specific contractual requirements of the VPLS service are critical. When evaluating different implementation strategies, the focus should always be on the most secure and reliable method for achieving the desired service outcome, rather than opting for simpler or less secure alternatives that might introduce unacceptable risks. Question 17. What factors determine the optimal VPLS encapsulation and signaling protocol selection for an Alcatel Lucent VPLS deployment when a customer specifies a particular service type and detailed traffic engineering requirements? Option A, the general availability of VPLS features on Alcatel Lucent equipment, without specific consideration for the customer's stated service type and traffic engineering objectives. Option B, the signaling protocol that is most commonly deployed within the provider's existing network, without verifying its suitability for the customer's specific VPLS service. Option C, the customer's specified VPLS service type and traffic engineering requirements, in conjunction with the capabilities of the chosen signaling protocol to support these specific needs. Option D, the provider's preference for the simplest VPLS encapsulation method, irrespective of detailed traffic engineering requirements. The correct answer is C. The customer's specified VPLS service type and traffic engineering requirements, in conjunction with the capabilities of the chosen signaling protocol to support these specific needs. Explanation. Scenario analysis. This scenario presents a common challenge in network design where a service provider must balance the need for efficient resource utilization with the strict requirements of a customer's virtual private LAN service, VPLS, deployment. The customer has specified a particular VPLS service type and a set of traffic engineering parameters. The challenge lies in selecting the appropriate VPLS encapsulation method and associated signaling protocol that not only meets the customer's stated requirements, but also aligns with the provider's operational capabilities and the underlying network infrastructure. Misinterpreting or inadequately addressing these requirements can lead to service degradation, increased operational overhead, or even non-compliance with service-level agreements, SLAs, which could have contractual and reputational repercussions. The provider must demonstrate a thorough understanding of VPLS principles and their practical implementation within the Alcatel Lucent ecosystem. Correct approach analysis. The correct approach involves a detailed analysis of the customer's VPLS requirements, specifically focusing on the desired service type, e.g., Martini or Compella, and the traffic engineering needs. For Martini VPLS, the provider would typically consider using MPLS as the transport mechanism, leveraging Label Distribution Protocol, LDP, or Border Gateway Protocol, BGP, for label distribution. If the customer's traffic engineering requirements are complex, involving specific path selection or bandwidth guarantees, then BGP with extensions for MPLS traffic engineering, MPLSD, becomes a more suitable choice for signaling. This approach represents best professional practice because it directly addresses the customer's stated needs by selecting the VPLS encapsulation and signaling protocol that best supports the specified service type and traffic engineering objectives. It ensures that the VPLS is configured to deliver the expected performance and functionality, thereby meeting contractual obligations and customer satisfaction. Incorrect approaches analysis. One incorrect approach would be to solely prioritize the simplest VPLS encapsulation method, e.g., assuming Compella VPLS without considering traffic engineering needs, without a thorough evaluation of the customer's traffic engineering requirements. This is professionally unacceptable because it risks failing to meet the customer's performance expectations, potentially leading to SLA breaches. It demonstrates a lack of due diligence in understanding the full scope of the customer's needs. Another incorrect approach would be to select a signaling protocol based purely on the provider's existing network infrastructure, without verifying its compatibility with the chosen VPLS encapsulation and the customer's traffic engineering requirements. This could result in an unstable or inefficient VPLS deployment, as the signaling protocol might not adequately support the necessary label distribution or traffic engineering functions for the specific VPLS service. This failure to align the signaling mechanism with the VPLS service and customer needs is a significant professional oversight. A third incorrect approach would be to overlook the specific VPLS service type requested by the customer and proceed with a generic configuration. Different VPLS service types, e.g., Martini vs. Compella, have distinct characteristics and transport requirements. Ignoring this distinction can lead to fundamental misconfigurations that prevent the VPLS from functioning as intended, directly violating the customer's explicit service definition. Professional reasoning. Professionals should approach VPLS design by first meticulously gathering and understanding all customer requirements, including the desired VPLS service type, traffic engineering objectives, and any specific performance metrics. This should be followed by an assessment of the provider's network capabilities and the available Alcatel Lucent VPLS features. The next step involves mapping the customer requirements to the most appropriate VPLS encapsulation method and signaling protocol, considering factors like scalability, resilience, and traffic engineering support. A thorough validation and testing phase is crucial before service activation to ensure all requirements are met and the VPLS operates as expected. This structured, requirement-driven approach ensures that the deployed solution is not only technically sound, but also fully aligned with customer expectations and contractual obligations. Question 18. When evaluating the implementation of a virtual private LAN service, VPLS, on an Alcatel Lucent network to support multiple customer traffic classes with distinct quality of service (CoS) requirements. Which of the following configuration strategies best ensures adherence to service-level agreements and regulatory compliance for differentiated traffic handling? Option A. Implementing comprehensive ingress and egress CoS policies on provider edge P devices, including traffic classification, marking, appropriate queuing mechanisms, and policing, tailored to the specific traffic profiles of each VPLS instance. Option B. Applying a single, uniform CoS policy across all VPLS instances, irrespective of individual customer traffic characteristics or service criticality. Option C. Relying on the inherent multipoint-to-multipoint nature of VPLS to automatically prioritize traffic without explicit CoS configuration on any network devices. Option D. Configuring CoS policies only on the ingress PE interfaces, assuming that traffic prioritization at the entry point is sufficient for all downstream network segments. Correct answer is A. Implementing comprehensive ingress and egress CoS policies on provider edge P devices, including traffic classification, marking, appropriate queuing mechanisms, and policing, tailored to the specific traffic profiles of each VPLS instance. Explanation: Scenario analysis. This scenario presents a professional challenge in network design and implementation where a service provider is tasked with delivering a virtual private LAN service, VPLS, that must adhere to specific quality of service, CoS, requirements for different traffic classes. The challenge lies in ensuring that the VPLS configuration accurately reflects and enforces these CoS policies across the Alcatel Lucent infrastructure, particularly when dealing with the complexities of multipoint-to-multipoint connectivity inherent in VPLS. Misconfiguration can lead to service degradation, customer dissatisfaction, and potential breaches of service-level agreements, SLAs, which have regulatory implications. Correct approach analysis. The correct approach involves a thorough understanding of VPLS CoS mechanisms within the Alcatel Lucent framework, specifically focusing on how traffic classification, marking, queuing, and policing are applied at the provider edge P and provider P devices. This includes correctly configuring ingress and egress CoS policies on the VPLS interfaces, ensuring that traffic is classified based on defined criteria, e.g., DSCP values, marked appropriately, and then subjected to appropriate queuing mechanisms, e.g., strict priority, weighted fair queuing to guarantee bandwidth and low latency for critical traffic. This aligns with regulatory expectations for service providers to deliver services as per advertised SLAs and to maintain network integrity, preventing congestion from impacting critical services. Incorrect approach is analysis. One incorrect approach would be to assume that VPLS inherently provides CoS without explicit configuration. This is a failure to understand the operational nuances of VPLS and the need for granular control. Ethically and regulatorily, this could lead to a breach of SLA commitments, as critical traffic might not receive the guaranteed performance. Another incorrect approach would be to only configure CoS on the ingress PE interfaces, neglecting the egress interfaces or the P devices. This would result in traffic being prioritized upon entry, but potentially being dropped or experiencing congestion within the core network or upon egress, again violating SLA promises and demonstrating a lack of comprehensive network management. A third incorrect approach would be to apply a generic CoS policy across all VPLS instances without considering the specific traffic profiles and requirements of each customer or service. This would fail to differentiate between critical and non-critical traffic, leading to potential performance issues for high-priority services and a failure to meet the diverse needs of the customer base, which could be viewed as a failure to provide equitable service. Professional reasoning. Professionals should adopt a systematic approach to VPLS CoS configuration. This involves 1. Understanding customer requirements, clearly defining the CoS needs for each VPLS service, including bandwidth, latency, jitter, and packet loss targets. 2. Alcatel Lucent VPLS CoS design, leveraging the specific CoS features and capabilities of the Alcatel Lucent platform, including traffic classification, marking, queuing, and policing. 3. End-to-end configuration, ensuring that CoS policies are consistently applied across all relevant network elements, from ingress PE to egress PE and across the core P network. 4. Verification and monitoring. Implementing robust testing and ongoing monitoring to validate that CoS policies are functioning as intended and to identify any deviations from SLA targets. 5. Documentation. Maintaining detailed documentation of the CoS configuration for audit and troubleshooting purposes. Question 19. Process analysis reveals that a telecommunications provider is deploying a virtual private LAN service, VPLS, using Alcatel Lucent equipment to offer dedicated Layer 2 connectivity to multiple enterprise customers. A critical requirement is to ensure that traffic from one customer's network segment is strictly isolated from all other customer segments within the VPLS, preventing any form of inter-customer communication or data leakage. Which of the following configuration strategies best upholds the strict traffic isolation requirement within the VPLS framework? Option A. Utilizing a single VPLS instance for all customers and configuring the Alcatel Lucent equipment to broadly permit inter-customer traffic forwarding, with the expectation that customers will manage their own internal firewalls for security. Option B. Configuring the VPLS with a single shared service access point, SAP, that all customer edge devices connect to, relying on customer-provided LAN tags for differentiation within the VPLS. Option C. Implementing VPLS with distinct service access points, SAP, for each customer's connection to the VPLS, ensuring that each SAP is configured to only accept and forward traffic associated with its designated customer. Option D. Deploying VPLS without any specific configuration for traffic isolation, assuming that the inherent nature of VPLS inherently segregates customer traffic by default. The correct answer is B. Configuring the VPLS with a single shared service access point, SAP, that all customer edge devices connect to, relying on customer-provided VLAN tags for differentiation within the VPLS. Explanation. Scenario analysis. This scenario presents a professional challenge in network design and implementation, specifically concerning the security and isolation of customer traffic within a virtual private LAN service, VPLS, deployment. The core difficulty lies in ensuring that the VPLS, while providing a seemingly unified Layer 2 network, maintains strict traffic separation between different customer tenants. Failure to do so can lead to data breaches, service disruption, and noncompliance with service-level agreements, SLAs, and potentially regulatory requirements for data privacy and security. The need for robust isolation is paramount, especially in multi-tenant environments where trust between tenants is not assumed. Correct approach analysis. The correct approach involves implementing a robust VPLS configuration that leverages the Alcatel Lucent platform's capabilities for traffic isolation. This typically includes the use of unique service access point identifiers, SAP ID, for each customer's connection to the VPLS, and potentially the configuration of specific VLAN tags or other Layer 2 identifiers to differentiate traffic at the network edge. The VPLS itself is designed to create a logical Layer 2 broadcast domain, but the underlying configuration must ensure that the forwarding plane correctly segregates traffic based on these identifiers, preventing any form of inter-customer leakage. This aligns with best practices for network virtualization and multi-tenancy, ensuring that each customer's traffic remains within their designated virtual network segment, thereby upholding data confidentiality and integrity. Incorrect approach is analysis. One incorrect approach would be to assume that the inherent nature of VPLS automatically provides complete traffic isolation without explicit configuration. This overlooks the potential for misconfiguration or the need for granular control. Relying solely on default settings or a superficial understanding of VPLS can lead to unintended traffic sharing, violating the principle of tenant isolation. This is a regulatory and ethical failure, as it compromises the security and privacy of customer data, potentially leading to breaches of confidentiality and noncompliance with data protection regulations. Another incorrect approach would be to implement VPLS without considering the specific security requirements of each customer. Different customers may have varying levels of sensitivity for their data, and a one-size-fits-all approach to VPLS configuration can be inadequate. Failing to tailor the isolation mechanisms to meet these diverse needs can result in a security posture that is insufficient for some tenants, again leading to potential data breaches and regulatory noncompliance. A third incorrect approach might involve using a single, shared SAP for multiple customers within the VPLS. This fundamentally undermines the concept of isolation, as all traffic would enter the VPLS through the same logical point, making it difficult, if not impossible, to distinguish and segregate traffic effectively. This is a direct violation of the principles of secure multi-tenancy and would almost certainly lead to data leakage and severe security and regulatory implications. Professional reasoning. Professionals must adopt a proactive and meticulous approach to VPLS design and configuration. This involves a thorough understanding of the Alcatel Lucent platform's VPLS features, particularly those related to traffic segregation and security. Before deployment, a detailed assessment of customer requirements, including their security and privacy needs, is essential. The configuration should then be meticulously planned and executed, with a strong emphasis on verifying that traffic isolation mechanisms are correctly implemented and functioning as intended. Regular auditing and testing of the VPLS configuration are also critical to ensure ongoing compliance and security. This systematic process, grounded in a deep understanding of the technology and its implications, is key to delivering secure and compliant VPLS services. Question 20. Market research demonstrates that enterprise customers are increasingly seeking flexible and scalable network solutions. When designing a virtual private LAN service, VPLS, for a new multi-site enterprise customer with diverse connectivity needs and a projected growth in intersite traffic, which of the following approaches best aligns with providing a robust, future-proof, and cost-effective VPLS deployment? Option A. Deploy a VPLS solution based solely on the number of sites, selecting the most complex configuration to ensure all potential future needs are met. Option B. Prioritize a fully meshed VPLS architecture to ensure maximum redundancy and direct connectivity between all sites, regardless of current traffic volumes. Option C. Conduct a detailed analysis of current and projected traffic patterns, site interdependencies, and scalability requirements to select the most appropriate VPLS topology, which may include a hub-and-spoke or a partial mesh design if sufficient. Option D. Implement a basic VPLS solution with minimal features to reduce initial deployment costs, assuming the customer can upgrade later if needed. The correct answer is B. Prioritize a fully meshed VPLS architecture to ensure maximum redundancy and direct connectivity between all sites, regardless of current traffic volumes. Explanation. Scenario analysis. This scenario presents a professional challenge in selecting the most appropriate virtual private LAN service, VPLS, deployment model for a new enterprise customer. The challenge lies in balancing the customer's stated requirements for performance and scalability against the inherent complexities and potential cost implications of different VPLS architectures. A hasty or uninformed decision could lead to service dissatisfaction, increased operational overhead, and potential noncompliance with service-level agreements, SLAs, all of which carry significant business and reputational risk. Careful judgment is required to align technical capabilities with business objectives and regulatory considerations. Even if not explicitly stated in the syllabus, the underlying principle of providing a compliant and effective service is paramount. Correct approach analysis. The correct approach involves a thorough assessment of the customer's current and projected traffic patterns, bandwidth needs, and the geographical distribution of their sites. This assessment should then be mapped against the capabilities and limitations of different VPLS deployment models, such as a single-site VPLS, a multi-site VPLS with a central hub, or a fully meshed VPLS. The chosen approach prioritizes a scalable and resilient solution that can accommodate future growth without requiring a complete redesign. This aligns with best professional practice by ensuring the deployed service is future-proof, cost-effective in the long run, and capable of meeting evolving business demands. It also implicitly supports regulatory compliance by ensuring the service can be managed and monitored effectively, which is a foundational aspect of many telecommunications regulations. Incorrect approaches analysis. One incorrect approach would be to solely focus on the lowest initial cost, selecting a VPLS model that is the cheapest to implement but lacks scalability or resilience. This fails to meet the professional obligation to provide a robust and sustainable service, potentially leading to future upgrade costs and service disruption. Ethically, it could be seen as misrepresenting the long-term value of the service. Another incorrect approach is to over-engineer the solution by implementing the most complex and feature-rich VPLS model without a clear business justification. This can lead to unnecessary operational complexity, higher maintenance costs, and a steeper learning curve for the customer's IT staff. From a regulatory perspective, while not directly violating a specific VPLS rule, it demonstrates a lack of professional due diligence in tailoring the solution to the client's actual needs, which can indirectly impact compliance with service delivery standards. A third incorrect approach is to ignore the customer's stated performance requirements and deploy a basic VPLS solution that might meet minimal connectivity needs, but not the desired quality of service. This directly violates the professional duty to deliver a service that meets agreed-upon specifications and SLAs, potentially leading to contractual breaches and regulatory scrutiny regarding service delivery. Professional reasoning. Professionals should adopt a consultative approach, beginning with a deep understanding of the customer's business objectives and technical requirements. This involves active listening, asking probing questions about current and future needs, and collaboratively exploring different VPLS architectures. The decision-making process should involve a comparative analysis of the pros and cons of each viable VPLS model in relation to the customer's specific context, considering factors like scalability, resilience, manageability, and total cost of ownership. This structured approach ensures that the chosen solution is not only technically sound, but also strategically aligned with the customer's business goals and adheres to professional standards of service delivery.